Let's say that we wanted to add the two vectors p and q together and find their resultant vector r. We already know about the parallelogram law, which lets us place these vectors in a tail-to-tip fashion and use their intersection to find the resultant vector r. The addition of vectors p and q would equal the resultant vector r. And we do want to note here that adding vectors p and q are not simply equal to the summation of the scalar quantities p and q. In other words, if vector p had a value of, let's say, 10 pounds and vector q had a quantity of 5 pounds, the resultant is not necessarily 15 pounds. The direction of the vectors that add up to the resultant vector r influence what the magnitude of r will be. So the parallelogram law that we used here does not depend on which vector is added first. We could, if we wanted to, add vector q plus vector p, or we could add vector p plus vector q. Both vectors will still equal the resultant vector r. This means that vector addition is associative and commutative. We can also use trigonometry to find the resultant vector of two or more vectors. And this is somewhat similar to the parallelogram law, in which you still draw the vectors in a tail-to-tip fashion. So let's say that we had two forces acting on a particle A. These vector forces were P and Q. If we wanted to find the resultant of these two forces acting on the particle A, we could take vector Q and move its tail to the tip of P, and then we would draw an arrow from the particle to the tip of Q. Now, as you can see, we have a triangle. These vectors have formed a triangle. And if you draw these vectors to scale, let's say on graph paper or some computer-aided drafting software, you could graphically find the resultant vector r. And you can also use trigonometry to find the values of vectors and their directions, and that's something we'll see in future lectures. Now let's take a look at this example. What if we wanted to subtract vectors? Well, technically there's never really subtracting vectors. Since all vectors have a magnitude and a direction, we can assign vectors as either positive or negative. To add negative vectors, we simply add the positive and negative vectors together. In this case, vector q seems to be going in the negative x and y direction, right? It's going to the left and to the bottom. We can apply the triangle or parallelogram rule to find the resultant of these two vector forces. We will use the triangle rule and move vector q's tail to the tip of vector p, and then we'll be able to find the resultant vector r. So what if we wanted to add more than two vectors together in trying to find a resultant vector force? Well, vector addition allows us to add as many vector forces as we want using something called the Polygon Rule. And the Polygon Rule follows the same rule as the triangle rule. We take each vector and align them in a tail-to-tip fashion and then draw a resultant vector from the particle to the tip of the last vector added. This will give us our resultant vector. You could also add two of the vectors first and then add the third vector to the resultant of the two vectors, and this will still give you the final resultant vector r. Now let's say that we had a particle A, this little gray dot here, that was being exerted upon by a force of P. The force was acting to the right, and the force had a magnitude of 2 newtons. If we wanted to double the force on this particle by a factor of 2, we could add another vector p to this diagram. This would give us a new vector of 2p, which is simply the addition of two p vectors, two original p vectors. This 2p vector means that the force being exerted on this particle A is twice as much as the original p force and in the same direction. In other words, the new force being exerted on particle A is now 4 newtons instead of 2 newtons, and it's acting to the right. The 2 here would be a scalar quantity, and the vector quantity would be p. If we wanted to triple the force on this particle, we could add yet another vector p, and the resultant of these three vector forces would be 3p. This means that the force being applied on the particle is now 3 times as much as the original vector p. The new force on this particle is now 6 newtons instead of the original 2 newtons, and is still acting to the right.